Yeah, hello. Good morning, everyone. Yeah, it's our pleasure to have Kaitlin here to talk about her work on generative modeling with quantum neurons. Yeah, so quantum generative modeling is becoming a very big field now. Like people just started to look into unsupervised machine learning, and generative modeling is one of the aspects that people go into. But so far the model that we had kind of like linear per se because we didn't have not like non-linear activation function and because like all the quantum machines quantum mechanics is essentially linears. And over here like Kaitlin will show how we can incorporate non-linearity in the quantum generative model. And I guess like she will try to tell us what's the benefit of having nonlinearities in the quantum generative modelers. And I guess Kaitlin, you can take over it and start your presentations.
Great. Yeah, happy to. Thank you all for being here so early in your morning when it's in my evening. Um, I'm going to talk to you today about generative modeling with quantum neurons. I'm a PhD candidate currently at the University of Oxford, and I've basically spent maybe the last 2 or 3 years now very much going in deep with thinking about quantum generative modeling. So I'm happy to answer any questions even outside of this presentation that you might have on classical generative models or quantum generative models. I can't promise that I can answer every question perfectly. I don't have all of the knowledge, but I can do my best. And today, I hope that you learn at least a couple of things. I'm going to go a little slowly because I don't really know everybody's background in terms of if you even know what a generative model is or if you know how this looks like in quantum. So I'll probably end up starting there. So I'll start with a brief introduction into generative learning. Again, feel free to jump in and ask questions anytime. I'm going to give a definition of a quantum neuron subroutine. I think in the quantum literature, there tends to be multiple definitions of what a quantum neuron is or what we're defining it to be. And I don't think yet we've even come up with what is the optimal, let's say, quantum neuron. So I'm just going to tell you the quantum neuron that we are working with, like in this context. And hopefully I can kind of, encourage you to think that combining these two things is interesting. This is like a kind of novel approach because typically in quantum generative modeling, we do have certain quantum models where we don't see nonlinear activations throughout the input. We only see nonlinearity when we take measurement at the end. I'll talk more about this. But I want to kind of motivate that maybe combining generative learning and then quantum neurons that we typically see in maybe like more quantum supervised learning, that combining these things is interesting. I'm going to show some key results that my team has gathered, which have been really interesting. I think, though, that there is a lot more benchmarking and understanding from a theoretical perspective that can be done. So I'm going to give some future directions. So I will start with what I define as the generative learning process or what I've come to understand it. So we have some data points, and this training data could be measurements, it could be images, like these could be quantum measurements, but typically a lot of times we work with classical data, especially in industry at the moment. So you could think of like a classical image set, and these can be your data points. Then the goal of a generative model is actually to approximate a probability distribution over this data. So typically this training data will come, like there'll be, we'll think of them as like randomly sampled points from this underlying true distribution that we don't know. And our goal is that we would like to approximate this underlying true distribution with these few samples that we have. So in order to do this, we'll train some kind of parametrized model with a cost function, where that cost function is usually some kind of similarity distance between the training data and the samples that we're then able to take or generate from our probability distribution or our approximated distribution from the model. And so our cost function, like typical cost functions, are like KL divergence is typically used for very small scale models. We know that KL doesn't scale well. We know that there's also problems with the maximum mean discrepancy that I have here as well. The Wasserstein distance has been kind of proposed. The TV distance has been proposed. And it's still very much an open research question in both classical and quantum to develop cost functions that are scalable and efficient. But typically, it's minimizing some sort of similarity between the output samples that we get from the model and the training data that we have. We can then optimize the parameters in our model using some kind of gradient descent algorithm. So this could be ATOM. It could be a gradient-free algorithm like particle swarm optimization. It really depends. Usually this kind of optimization is a hyperparameter in itself of what you would choose. And so then you can train your model for, so many iterations. And once you do, you can ask a couple of questions. The first is, how well did the model learn this ground truth probability distribution from the finite set of samples that you gave it? And answering this question from both a theoretical perspective and just benchmarking simulation perspective is actually can be quite difficult. But then you can do something else. You can ask, how well does the model perform on a particular task? And because I'm talking about generative learning, you could assume that for this particular task, I mean data generation. So typically, after we've trained this model to, approximate the probability distribution over our data, we want to be able to generate some kind of data that is not necessarily from that training distribution, but is similar in features to the things in that training distribution, meaning that it's from that ground truth or underlying distribution. That's actually a behavior that we call generalization. But in industry today, we see generative models kind of everywhere. I think it began more so with image generation. There's like there's like a website where you can basically just generate fake people. If you've seen like deep fakes of Tom Cruise, that's, a generative model. We see it in molecular discovery, so like generating new molecules, using some kind of chemistry optimization. We see this a lot in combinatorial optimization, also for finance. We see this with natural language processing, which are very specific kinds of generative models. Basically, I mean, generative models, like there are many different kinds and there are many different training schemes. So I will put out there that this is one kind of training scheme that's most relevant for this talk. But there are also other kinds of training schemes that we would see to train generative models. So now, where does quantum actually fit into this? So in the last maybe 4 to 5 years, generative modeling has become an application for potential quantum advantage. I think I'm going to motivate to you a couple of reasons why we've chosen to look at quantum generative models specifically. I think a lot of people have done really important research to motivate that if we place a quantum circuit as our parametrized model in that generative learning scheme, we get kind of a nice natural fit. The first part of that natural fit is that quantum systems are universal approximators of discrete probability distributions. Because we know that we can approximate any probability distribution that we would like with our quantum states. This, by the way, doesn't mean we can learn any probability distribution. This just means we can express different probability distributions depending on how we parametrize different gates and the different gates that we use. But this in itself is important, right? Because quantum circuits express probability distributions. We need that. That's what a generative model is supposed to do. It's quite a natural fit. As well, so measurements of quantum systems are random samples from the probability distribution over those possible quantum states. So in this way, you could think of it as, generating samples from a generator is akin to taking quantum measurements. Again, quite a natural fit. Quantum systems can be transformed with parametrized operations. So these parametrized unitaries, can transform us from, one distribution to another distribution. You can kind of think about it like this. And we can compute gradients of these quantum circuits using the parameter shift rule. It doesn't mean that we can compute gradients efficiently, and we are, very much tools for training quantum circuits in general is still like a very much open field, and there are many open research questions. And so once we realized, that we could insert quantum into the learning process, we started developing what are these different ansatz, or like what are these different ways in which we can kind of formulate quantum circuits to create quantum generative models. Typically, it's a lot of poly rotations, entangling, parametrized entangling gates. There's been work where we try to adapt specifically the gates that we use to the hardware if we're trying to do something a bit more nisky. We've worked on, like all-to-all ansatzes where like every qubit is connected with every other qubit or entangled. There's like line topologies where basically just nearest neighbor qubits are connected. But typically when we have some kind of gate set in these different kind of topologies, and then we have this algorithm where we take our measurements and take our samples, and then we compute our cost, kind of like I showed you before in the generative process. Typically, this entire algorithm will refer to as a quantum circuit born machine. So that's what QCBM means here in this case. And I would say quantum circuit born machines are basically the most highly studied like quantum generative algorithm that exist. We can also have other kinds of ansatz though, that we've kind of labeled, I guess, something a little different, that would maybe be more closely resembled to a classical model. So one of these ansatzes is just a Bayesian ansatz, where we're basically feed forwarding information from previous qubits to later qubits, and we're able to approximate joint probability distributions over variables. So, classical Bayesian networks are something that we use all of the time. Quantum Bayesian networks or kind of the mapping to a quantum Bayesian network in this way has been developed. And in this case, you would only measure from the output or the final layer of qubits that you have. And today I'm going to talk to you about a repeat until success ansatz, so an RUS ansatz. And what's specifically special about this kind of ansatz is that we introduce nonlinear activations between qubits that are feed forwarding information. So it's similar-ish to a QCBM, especially in the way that it's trained. But it's also similar-ish to a Bayesian network in the way that we're feed forwarding information. But kind of the special magic of the RUS circuit is that it gives us this kind of step function power as we feed forward information. So it gives us like this nonlinearity. So now I'll go on to define this a little bit more formally. And this is what I would call the quantum neuron subroutine, which is the RUS circuit in itself. And it can be defined as this transfer of information from an input qubit to an output qubit through an RUS circuit. And not necessarily even just one input qubit, but an input state of maybe qubits in superposition to an output qubit through an ancilla. So it utilizes an RUS circuit, utilizes mid-circuit measurements of this ancilla to activate the nonlinear function on the parameters that get transferred from this input neuron or this input state of neurons to the output neuron. This is the actual RUS circuit. As you can see, it was introduced in this paper in 2017. When it was introduced as kind of like a very initial quantum machine learning, also like first classification and supervised problems. And it like a very small circuit of this was done. But the really interesting thing about this is that this circuit, you could think about it as approximating this Q of theta from this input state to this output qubit in this nonlinear activation function of arctan tan squared of theta. And you can actually ramp up this, you could ramp up the nonlinearity by having, Q of theta, Q squared of theta, Q cubed of theta, by basically like embedding these into each other. In our work, we only worked with Q of theta. So we kept the nonlinear, we didn't work with increasing the nonlinearity, but in this paper, it shows that you can do this. And so then we kind of coined a term called the Quantum Neuron Born Machine, because it's similar to the QCBM in the way that we take measurements from our output qubits, where these measurements are, random generated samples from the probability distribution that we're approximating via the Born rule of quantum mechanics. And then we're able to update our network in a similar way to the generative process that I showed in the beginning, where we'll compute a cost function between those samples that we generate and some samples from our training data. And we have our parametrized RUS circuits. I know that this graph or this chart may not be the most intuitive thing, but essentially you can think of the RUS circuits in the QNBM as like just many of those circuits tied together in multiple layers. So you can have a first layer, we Hadamard all of our inputs, and then from our input neurons, we then feed forward the information to our ancilla. On our ancilla, we then take a measurement, and we know that if we measure a 0, then we have success, and if we measure a 1, then we don't have success and we actually have to do another couple of operations, and then we have to repeat the circuit again. If we have success, we know that we have mapped the nonlinear activation function with the feed-forward information onto the output qubit. So in this specific quantum neuron born machine, we see a network layer structure of a 405, meaning that we have 4 input neurons in superposition, and we output that layer into 5 output neurons. And 0 just means that we don't have any in-between layers in this example. But so you could imagine that you could create larger networks with something like the QNBM. I won't lie that the scaling isn't fantastic. It's not as NISQY as the quantum circuit board machine. It requires O of E 2-qubit parametrized gates, where E is the total number of edges. You can think of as edge as like from an input neuron to an output neuron. And N is the total number of neurons in the circuit, so input, hidden, and output. But so the structure requires O of E 2-qubit parametrized gates, O of N 1-qubit parametrized gates, O of N 2-qubit and 1-qubit fixed gates, and then O of N of qubits, where only the N out, so the output neurons are actually the ones that are measured. So we do have quite a qubit overhead compared, let's say, to the QCBM, where the QCBM, the number of input qubits is equivalent to the number of output qubits that you measure. So now I'm going to get into some of our key results from what happened when we actually started to benchmark this model on a simulator. So the first thing that we did was we looked at a very simple generative task. So we asked, can this model approximate a constrained uniform distribution, where if you have bit strings, discrete bit strings of 0s and 1s, a constraint is simply like if you have the constraint of how many 1s you have, and that's all of those bit strings that have a certain number of 1s will all be like the same probability. And we used a cardinality-constrained in this case. So I believe for our different networks, our cardinality was the dimension or number of qubits that we used over 2 is what we used for our cardinality constraint. Yes. And then we used KL divergence as our cost function. Again, KL divergence isn't very scalable, and I wouldn't recommend that we keep using this once we scale up. But for these like small scale networks, it does just fine. We used an atom optimizer for 200 iterations. We basically trained these over different networks, and I'm about to show the data. But for 2 output neurons, we used 200 iterations, and then when we had more than 2 output neurons, we used 500 training iterations. Did this on the Qiskit simulator, and we used post-selection instead of actually doing the mid-circuit measurements, because at the time the mid-circuit measurement capabilities we didn't have the mid-circuit measurement capabilities. Now I think when we continue to do work on this, we actually have devices that are coming out with their simulators with mid-circuit measurement capabilities. And so this is some of the initial results that we had gotten from our work actually last summer, that we had put out, where we did different networks of input, hidden, and output layers. We saw a couple of things that were interesting. And again, like we don't understand fully how this model is biasing the learning process. I'm going to talk about that a little bit more later. But typically right now in the quantum generative modeling field, a lot of how we're approaching this work when we're designing new models is the first step is to, train them and to kind of see what happens. And it's somewhat of a similar approach that we've taken in classical black box machine learning. It's not an approach I love, but it's definitely a start. And so in the start that we did, we saw that when there were no hidden layers, we got the smallest KL divergences, which we want. We want a small KL divergence. We want our training data to be very similar to our sample data. And then we got the best precisions. And you could think of precision as just like, did we get samples that matched our cardinality constraint? So we want that to be close to 1. So with no hidden layers, we saw optimal performance. And when we had an input neuron that was 1 less than our output neuron, and then when we had, so basically similar numbers of input and output neurons, that's also when we saw really good performance. It didn't seem to have as much to do with the number of parameters that we gave the model as much as it did these kinds of structures, which is just something that's interesting. Then what we did is we compared it to the quantum circuit-born machine, which we knew to be kind of the state-of-the-art quantum model. We did this with 5 output neurons. We did 405 for the QNBM, and then just like 5 qubits for the QCBM. When we trained it on just like a standard uniform distribution, both the QNBM and the QCBM did, fine. The QCBM outperformed the QNBM by a bit. The uniform distribution is, quite easy to learn. We did this because we also then wanted to compare it to the constrained uniform distribution, which we know is more difficult for the model to learn. We saw that the QNBM was able to outperform the QCBM when we ran this over multiple trials, that the QNBM has a 3 times smaller error rate. It's interesting here because we're kind of we're showing training, we're also showing expressivity. We gave QCBM and QNBM a similar number of training resources, like the same number of training resources and a similar number of parameters. It's possible that the QNBM is more expressive than the QCBM at learning this distribution. We see for the uniform and the constrained, when we actually look at our loss, we see that the QNBM is able to kind of get beyond this plateau in expressivity that the QCBM reaches. It's possible that this is a expressivity problem. It's also possible that maybe this is a training problem. But because these QCBMs are so small, I wouldn't necessarily think it's like a barren plateau kind of training problem. And it seems more like it's a problem with expressivity. So potentially the QNBM with the same number of parameters as the QCBM is more expressive. And for the QCBM, we used an all-to-all odds-off. So we gave it actually, like full maximum expressivity. The difference between the QNBM and the QCBM is that the QNBM has these nonlinear activation feed-forward networks in between qubits. So this kind of pinpoints that nonlinearity is doing something that's interesting for us. We then also, in our more latest work, assessed the QNBM relative to the RBM, not necessarily to show, that quantum models beat classical ones. I don't think that any of this data, demonstrates quantum advantage, but just kind of as a benchmark. And so we trained a 405 QNBM as well as a 405 RBM. RBMs, I recognize I didn't go into depth with what those models look like. RBMs are restricted Boltzmann machines. They're more of a classical network that actually would be a little bit more analogous to a QNBM. In multiple papers in the literature, people will compare RBMs and QCBMs, which is why we ended up going with the RBM just for our first comparison. But we then trained these models on a discrete Gaussian distribution. We trained it on bars and stripes, which is what we typically would also use to train generative models. We saw that the QNBM, provided really great performance. The RBM did not do nearly as well as the QNBM. We even swapped resources for the RBM in the sense that we wanted to ensure, because the RBM does have a training algorithm that is different than the QNBM. The nice thing about the QNBM and the QCBM is that their training algorithms are very much the same, like similar, like same cost function, same way of sampling, same optimizer we can even use. Whereas with the RBM, classical models are trained differently than quantum models in many ways. So it's really difficult to have like a very fair comparison. So with the RBM, we tried to, hyper-parameterize, like tune it. Like we tried to optimize it in many different ways, and we still couldn't find an RBM that beat our QNBM. We also wanted to demonstrate that the QNBM has good learning potential. And I use the word learning here in a very like air quotes kind of way, because I think we're still, as a community in quantum machine learning and in classical machine learning, defining what we mean learning to be. As we are benchmarking and as we're, thinking back to learning theory, there's many different definitions. But here, I want to introduce this idea of our QNBM is able to get closer to that ground truth that I was kind of talking back in the beginning of the presentation than the distribution of the training data. And so the way that we show this is in the orange, we have just, like a kind of multi-mode discrete Gaussian probability distribution. We sample from this probability distribution. So in B, we take 200 samples. And then in C, we take 300 samples to approximate our distribution. And then what we show is this thing on the end of the true KL and the training KL. So the training KL is the KL divergence between our model's output samples, the distribution over those, and the samples of our training data. The true KL is the output of our model samples compared with just the overall true probability distribution. I know that I've said kind of samples and distributions interchangeably here. They're not. When I say that, I mean distribution over samples. If I've messed up and said samples and compared it with distribution, we're comparing distributions here when we're computing the KL. But what you can see is that kind of in the top plot in D, the training KL is lower than the true KL for the 200 sample case. But when we ramp it up to 300 samples and we give the model 300 samples of training data, we see that the true KL ends up dipping below the training KL, meaning that the model is actually getting closer to the true distribution than to the training samples, which is what many people would define as learning or define as generalization, which is great. Because our models here are so small, we did this a 506. So 6 being our output number of like output qubits, meaning that we just have a 2 to the 6th size space for our distribution. That's quite small. We really do need to scale up to larger distributions to be able to obtain a better understanding of what the learning potential of the model is. So something else that I just want to, briefly mention that we thought was interesting in our most recent work is that we talked about the simulatability of the QNBM, because we thought at one point that it's possible that our QNBM could actually be mapped to a classical Bayesian network. What we found out is that this is not true. We can actually not map our RUS ansatz to a Bayesian network. And we show some of the proofs and the results in the paper. But the thing that is actually most interesting about this is that the reason we cannot map it is due to the superposition of neurons in the previous layer. We actually show that if our input neurons are not in superposition, then this actually can be mapped to a Bayesian network. And I think what's so interesting about this is we're always looking for places, right, where quantum can provide some kind of enhancement. And typically we're looking for that enhancement in terms of a speed up. Or we're looking at least for some kind of, maybe this isn't an enhancement, but it's a separation. We showed like a very like clean separation between this kind of quantum model and like a classical Bayesian network. And basically that it's actually the quantumness of the model mathematically that allows us to do something that's a bit more interesting than a classical Bayesian network. So now I'm just going to give a bit of a summary. So maybe the main point here that I would like for you all to take away is that the QNBM is designed differently. It has different building blocks than like a typical quantum generative model would. Quantum generative modeling is still a very new field. It's very up and coming in terms of trying to understand how to best build quantum generative models. Right now, we're working with the modeled form in the generative algorithm. Perhaps there's ways we can adapt the training, perhaps there's ways we can adapt the data, but we're still also looking for like the best building blocks to build this kind of model. I think the QNBM, needs a lot more exploration in itself, but I would also just like to encourage folks to like take inspiration from how the QNBM was built, in the sense that maybe we can take different kinds of building blocks other than just simple poly rotations. And those are things that we can use to create quantum models. So something that we're looking into as a team is right now, actually, we'll have results very shortly of showing the QNBM on hardware, specifically trapped ion hardware with mid-circuit measurement capabilities. So actually not using post-selection. But I will say again, the QNBM is quite a there's a decent amount of gates. So doing larger networks is still quite difficult on today's hardware. So small networks. I think understanding this quantum classical separation more in depth is just something of interest, because typically we don't necessarily see that with the quantum models that we build, that there's like a very nice like cutoff between the quantum and classical that makes our model different from the classical analog. But so this leads to the question of like, what is the inductive bias of the QNBM? So if the QNBM is performing maybe better than the QCBM on certain kinds of problems, if we see that the QNBM is able to, memorize distributions, we see that it has good learning potential. When we put in the QNBM into this like generative learning process, how is it biasing the learning process? Like, what does the QNBM, the way that it's constructed, like, what is it trying to learn? Or what kind of solutions is it biased towards generating? What kind of probability distributions is it biased towards learning? And then this can maybe be broken down a little bit smaller into like, what is the inductive bias specifically of our building block of like the RUS circuit? So we could ask the question, are RUS circuits good QML building blocks? Oh, yes. I'm sorry, did.
I think there
Nope.
might just be some background noise. Yeah, I guess you can go first. Yeah, sorry about that.
Oh, no problem. I mean, I'm finishing up. And so so it leads to the kind of the ultimate question, or one of my ultimate questions that I would love to answer is, what are the optimal QML building blocks? I feel like moving forward in this direction for quantum models, but specifically quantum generative models, is a question of interest. So with that, I'll say thank you. I'll give a shout out to some of my research collaborators on this work, who worked with me at Oxford. Also my Oxford research group, who are actually, many of them work on trapped ion quantum computers. A shout out to my funding, and Marcello Benedetti, who works at Quantinuum, who was very beneficial on some external discussions for this work. And definitely, go check out the work. We have 2 papers now out on this. One on just introducing the QNBM, and then like a follow-up work on more about the learnability, the classical simulatability. And yeah, I'm happy to take any questions that anyone might have regarding anything from this or just generative modeling.
Yep. Thanks, Kaitlin, for the very nice talks on the work. So far I didn't see any question coming from the audience. Maybe I could like ask some questions while people just like trying to think of questions. Over here, you consider the repeat until success circuit as the building block, right? But then it's like over here you need to repeat the circuits, and like you have to make sure that your ancilla to be in measured in 0 state. I'm just wondering like how high is your success probability, and how do you deal with the fail attempt?
So I believe it's in the paper. If off the top of my head, I know that it's bounded by 7, which is a really weird number, but there is a nice proof that demonstrates this in terms of, if like bounded by 7, it is like it's only up to 7 times that you'll do this, and until you get the success that you would like. And then you asked the question.
Yeah, so that's like basically what.
Oh yeah, so if you fail, there's 2 operations that you would have to do, and then you would repeat the circuit again.
Yeah, so okay, so I kind of read through it. For the case where you have only one input data, then it's still fine. I could see the corrections. But then when you have a supervision, I saw that there's a correction term between the supervision of x, and I'm just wondering whether when you correct it, like the coefficient f will go away or not.
When you correct it, the coefficient.
Yeah,
Sorry,
so okay, maybe I could just go to the part. Yeah, so like when you have the supervision of the input state, then you will have extra like amplitude deformations in the input state.
Mhm.
So I'm just wondering like whether the 2 operations that you apply, like one is on the ancilla, the other one is on the output neurons, right? Whether that will also help to correct the amplitude deformations, or it doesn't matter at all.
Oh, that's a good question. So my immediate answer to you is I don't believe it matters.
Mhm.
But I think that's a thoughtful question, and I would like to look into it, and I will follow up with you on a for sure answer. I don't think it matters.
Okay.
But I'm gonna double check is my answer.
Right. Okay. Yeah. So I think the other question that I have is should be more intermediate, because over here you just assume that like the ambiguity deformations is like doesn't matter at all, right? But then over here you have to repeat it 7 times. But then it's like if you have noise in your circuit, like this, basically the information that you have in your quantum state is basically decaying, right?
Mhm.
So that means that you really need to have a circuit of very high fidelity in order to implement this kind of like structures, right?
Yes, I would not say that this is like a Nisky algorithm. Um, in the same way that maybe a QCBM could be seen as a Nisky algorithm. I also
Okay.
don't think I maybe my opinion is also that like a QCBM is also not a Nisky algorithm. I think it depends like are you just like it depends what you're looking to do.
Mhm.
I think for any larger scale generative modeling problem of like practical relevance, it's not a Nisky algorithm.
Right. Yeah, I completely agree on that. Yeah. So I guess that okay. I now I saw there's one question coming from the audience. Yeah. Jun Yong has a questions about like encoding of classical data in supervised quantum machine learning tasks. A part of the algorithm is about the encoding circuits. Is there such a notion of encoding for quantum generative modeling? Uh, of its typically or is basically is a basis encodings, or if other encoding scheme exists is constrained by the decoding scheme so that the sample output can be made sent in terms of the original classical data space. I think the questions is about the distinction between supervised and unsupervised machine learning, and whether you need to do encoding in unsupervised machine learning, and what kind
Yeah,
of like.
so yeah, no, I think I can try. So for the nice thing about quantum generative modeling, and I think this was one of like the big things at the beginning, is that we were like, we don't need to embed data in the same way that we do with supervised learning. So if we're dealing with purely classical data, the only time we actually ever use training data is in our cost function, which is quite nice. It would be different if we were maybe using some kind of quantum data and we were actually computing the cost on the quantum circuit itself. Because there are some like quantum generative models where instead of like taking samples and then computing the cost classically, you could compute the cost like with the quantum circuit and do some kind of like overlap if you have like your training data, like your training distribution, let's say, like uploaded or embedded into the quantum circuit. You could then like do an overlap, more of like a like kind of like a swap test to compute the cost, more of like a quantum kernel kind of cost. And in that case, you would need to like embed your probability distribution of training data like into the circuit. Right now, I would say that's not typically done, at least with the knowledge that that's not going to be something Nisky. Um, but I think that the nice thing about generative models in this form that I've presented is that you don't need to embed any training data. Because in unsupervised machine learning, you don't have labeled data like you do in supervised machine learning. Hopefully that answered the question, but happy to elaborate.
Um, yeah, actually, I have a follow-up question on this one because while as well machine learning, you didn't have like okay for generative modeling, you didn't have training kind of like you didn't have to encode classical data, right? In your quantum circuit, but you do need to consider the prior distributions, and just wondering what kind of prior distribution you use in your like experiment, your numerical experiment. Like, is it the
So
uniform one, uniform like superpositions or?
yeah, we use uniform superpositions like we just use Hadamarts. But it's an open research question for like what is the optimal prior distribution to use.
Mhm,
In my mind, the optimal prior is a prior that has some sort of bias towards like the structure in your data.
mhm.
But if we don't know the structure in our data, then it's difficult, right, to develop a prior like this. Um, Also, a lot of times we'll use randomly initialized parameters, like for our like our initial set, um, which I also think is not great. Like we know that when we scale up, we get like barren plateau phenomenon with randomly initialized parameters, and like when you just kind of randomly initialize, you're just kind of guessing in the dark. Um, it would be optimal if we develop more techniques where when we have sets of data, we can understand some sort of underlying feature or structure about that data, and then we're able to embed that kind of structure in like our initial ansatz or like our initial prior, like for the generative model.
Yeah, so for this one, I think I remember I came across a paper of trying to combine the geometric quantum machine learning with this basically extend the generative quantum machine learning to generative modeling. I saw they kind of like utilized the rotational symmetry of the image to design the answer that preserve this kind of symmetry and use it to train to generative modeling. Yeah, I think that this one is kind of a nice direction to go if people are interested on it. Yeah.
I think this is the main direction people are now trying to go. And
Yeah.
this is like the idea of like imposing the symmetry in the quantum circuit is the same thing as like encoding an inductive bias. Um, so I think the work that you're talking about, is it the work with tensor network born machines? Not with quantum circuits, but with like MPS, like matrix product states.
Okay, I didn't go, I couldn't give you an answer now because I didn't really like go into the paper itself. I just like kind of scan through it and see that they're basically trying to use some symmetry to design the answers for generative mode. Yeah, that's kind of the best that I'm kind of like understand paper. Yeah.
Yeah, I think that paper, if we're talking about the same one, I think that one was on like tensor networks, which are like
Okay.
quantum inspired models. And I
Mhm.
think right now it's like active progress to try to like convert that kind of figure out how to like place or impose that kind of symmetry in like the quantum models. But yeah, I think in
Right.
general in quantum machine learning, we're like going towards it's really good. I think this is like a good way of moving. Like we're going towards this approach of like imposing inductive biases like in
Mhm.
these models, or like also just trying to understand like the biases that are innately kind of created from these models, similar to like we're trying to understand them in classical machine learning.
Right. Yeah. So I guess this is important because, well, in from classical machine learning, we already have a so-called like no free lunch principle, and I guess it should apply to like quantum machine learning. And I think like Zoe also like shows some things about this like non-free lunch principle. Okay, then we have another question from the audience. Your model shows better training performance than the QCBM, but I guess with the mid-circuit measurements, the required time to draw a single samples from the trained model will be longer. Have you thought about the potential trade-off between training speed and the speed of drawing sample from quantum generating models? For example, classical generating models are often trained once using a computing cluster and then deployed to many end users who run them on their device. Yeah.
I think this is a very valid question, um, in the sense that it takes a long time to train a QNBM. Um, Mostly because of actually like the large Hilbert space of the model. So like when we're running it like on a cluster, like on a supercomputer, we just have really large matrices that we're dealing with. Even just for like a small output layer of qubits, right? Because like for a QCBM, you have like a Hilbert space for if like 5 qubits, your Hilbert space is like 2 to the 5th. Um, Whereas like for a like a QNBM, you have like 5 in your output and then 4 in your input plus 1 ancilla. So you have 9 qubits that you're working with. So that's already creating like a lot, like there's like a lot larger, right, of like a space versus like the QCBM. And so this is actually why like it takes quite a long time to train them. I think that is more of the training speed maybe issue with like actually training them on the simulator. On the actually doing this on the hardware, right? That would maybe not be the issue. In terms of using mid-circuit measurements, I'm not necessarily sure it would take that much longer, depending on, I feel like this is like a very hardware, I could be totally wrong. This seems like a very hardware dependent issue in terms of like how fast the mid-circuit measurements are. Because even with QCBMs, like, right, the larger that you have, the more qubits that you have to have very deep networks of QCBMs. Like you can have a decent amount of parameters. Um, I think with the QNBM, you might be able to save a bit on the number of. Okay, maybe I shouldn't make that claim. Maybe I shouldn't say that's true because I'm not fully sure. I'm not fully sure that's true. Um, It's an interesting question to consider when you're at large scale, if there would be any kind of like speed advantage or disadvantage to using like a QNBM or a QCBM. I will say, in the niceness, I guess, about machine learning is if you get a better solution with the QNBM and you just have to wait a little bit longer, no one's going to care as long as you get to the better solution. Which is why it's an interesting thought of like this like quantum algorithms, quantum supremacy, like quantum advantage being a speed up thing. Because in some like very practical industry problems, and this is kind of why in quantum generative modeling we're moving also towards a word called practical quantum advantage, which is also just can you generate better solutions than a classical model or any other kind of model, maybe slightly less independent of time. Only because, if it takes an extra day to run your model, but you end up getting to the better solution that's going to make your customer a lot of money, it doesn't really matter that it took the extra day. But for some problems, it might matter that it took the extra day. So like it very much depends on the application at that point. That was a long-winded answer, but hopefully it was useful in some capacity.
Yep. Yeah. Hold on. Maybe. Yeah. A lot of follow-up questions on this. Can all the mid-circuit measurement in QNBM be done simultaneous, or there are some that had to be come before, after, or after another? Basically, the sequence of mid-circuit measurement that you have to do, like whether you can do simultaneously or there's a sequence that you have to be performed.
So I feel like this depends. Does this? I don't. I feel like this depends on the hardware, but again, I could be wrong because I'm not an architecture person. In like this might sound bad, but I send the algorithm in and I'm like, okay. Um, so somehow it gets executed on the hardware. And I'm not sure which gate operations actually, get executed in a certain order. And also, a lot of times, if you're actually running this on hardware, right, there's like a native gate set that it will be compiled into, and then certain things will be run in that order. So from like a very strict hardware perspective, I guess my answer is I don't know the order of how everything gets done. But if you're just kind of talking about from like a theoretical level of like you compute the mid-circuit measurements from like one input neuron to the output neuron, I don't think it matters. They could in theory be all. I actually don't know. That's a good question. In theory, I feel like they could all be done simultaneously in the sense that they're all of the information is going to different output neurons. But at the same time, no, because we're only using one ancilla qubit. So my final answer is no. If we were using multiple ancilla qubits, then the answer is, I think, yes. Because then we would be able to we would be able to do them all simultaneously. But we use one ancilla qubit and then we reset the ancilla qubit each time. So that's my final answer. If we use multiple ancilla qubits, it could be done in parallel, I think.
As in like, okay, I think you kind of like mentioned the good point. Okay, I'm not too sure whether this is a valid questions or not, but I know in like photonic quantum computations, people use like gate teleportation to teleport the nonlinear gates into the quantum computations, and wondering whether you can remove all these like measure until success circuits by like incorporating like gates measurements, so that all of this like kind of like image circuit measurement could be done apart from the computation itself, or whether it's like it's not possible because their structure is fundamentally different.
Are you asking if like
Yeah, because over here you have kind of the mid circuit measurements, and then you measures, and then when you get the when you get the kind of like zero state from ancilla, then it kind of like tell you that you'll get this kind of implement like your nonlinear activation functions as implemented successfully on the output neurons, right? Yeah, and it's from like it seems to me that this have a similar structures with the measurement induced non-linearities in photonic quantum computations, and how people kind of like and this measurement based non-linearities also realized using kind of like measurements, and then when you get a kind of signal, then you know it's success, and the success probability is less than one. How people kind of deal with this kind of issue is to use gate manipulations. I guess this one is the scheme designed by Isaac Chuang, where you can kind of like remove this kind of like probabilistic gates outside and do this repeat until success measurements at the outside, and then teleport back when you get the right one.
That's interesting. Okay, so I don't know anything about that in terms of
Oh,
like
okay.
how that
Maybe it's
incorporates into QBM, but that's cool. And I should look into it. Do you know what it's specifically called, like that method?
Oh, okay. So I know it's like the method is called quantum gate manipulations. Like normally we have a state manipulation,
Okay.
right? But that one is gate manipulation. I could like send you the papers by Isaac Chuang like after
Sure.
the talks, and see like okay, I'm not too sure whether it's kind of valid or not, but it's just something in my mind.
Yeah, no, that's
Um
great.
yeah.
Yeah, that sounds great.
Okay, I guess like we should have time for one final questions. Okay, seems like there's not much question for now. Okay, maybe I could just ask the last questions. I know from FPS, right? Like Krista, like Zofra from IBM, like she mentioned that they kind of be able to show Bernbet tools in QGANs, and it's like if I'm not wrong, Suparno also shown like kind of shown like Bernbet tools in QCBM. Do you think that this your models will also suffer from Bernbet tools, or because over here it seems to me that QNBM and QCBM have different kind of structures, right?
Yeah. I mean, so I think an open question is, does the QNBM suffer from barren plateaus? Because it has like a different structure with the mid-circuit measurements. Um, my hypothesis is probably yes, if we start from randomly initialized parameters. I
Okay.
think that when you start from randomly initialized parameters, you're kind of opening yourself up to like barren plateaus. Like from all
Mhm.
the barren plateau work that I've seen, it feels like every work, and I don't know for sure because I haven't read all the works, but it feels like if we have randomly initialized parameters, we get barren plateaus. If we fix some kind of prior that has structured our data, we don't get barren plateaus.
Okay.
So I feel like that's what we should be going towards.
Yeah.
But it would be interesting to investigate the QNBM like at larger scales and see that if we do see this kind of phenomena,
Mhm.
I expect that we probably would. But I think that's something that's quite interesting about the QNBM didn't mention is that the trading for it is actually it's more unstable than QCBMs. Um,
Okay.
but I think what's interesting, maybe because it's so unstable, it seems like it has these random kicks. Like it will like kind of like plateau a little bit like a QCBM, and then all of a sudden, like random kick, and it'll start like the cost will start decreasing again. So there's something in the QNBM structure that's like giving it this random kick. Maybe because of that, it would be less likely to have barren plateaus.
Right. Okay. Great. Thanks for answering all of our questions. There are like quite a lot of questions from the audience and from me. Yeah, I think you kind of like answer all of the questions very nicely. For now, so I didn't see any question coming from the audience, but I guess if they have any further question, they will email you to kind of clarify the things in the talk. And now it's 10, maybe we can like stop the presentation. And thanks again for Kaitlin for like speaking in our seminars, like, and introduce us this kind of new structures in generative modeling. Yeah. Thank you
No
guys. See
problem.
you. Bye.
Thank you, everybody. Have a good day.
Yep. Bye bye.